Okay, kids, today we're going to continue on writing where the electrons are, and today we are going to look at orbital diagrams. The other video we talked about electron configuration and noble gas configuration. Now we're going to use a different diagram to describe the location of the electrons. I showed you this picture last video. It's basically an orbital or an energy diagram, and it's showing you can see the different sublevels as well as energy increasing as you go through higher and higher sublevels. Okay, when we do orbitals, instead of boxes, we are going to draw lines. Okay, and we have rules for filling orbitals. Okay, so first of all, before I talk about the rules, let's talk about our orbitals. We saw pictures of our orbitals last video, and instead of using the actual pictures, we're going to use lines to represent the orbitals. Okay, we are going to use arrows to represent the electrons, either an up arrow or a down arrow. Okay, and the up arrow versus the down arrow just represents a different direction in spin. Okay, and we know from our last lesson that each orbital can hold 2 electrons. We also know that the S will have 1 orbital, the P will have 3 orbitals, the D will have 5 orbitals, more, and the F will have 7. Okay? So we are going to use those lines to represent orbitals. The arrows are going to represent electrons, and the 2 different up or down will represent the spin. Okay? So that's how we're going to draw orbital diagrams, but we're still going to read the periodic table like a book. Okay, now let's look at our rules for filling orbitals, okay? And these are important, and you have to know these. The first one is called off-ball principle. What it's saying is that electrons will occupy the lowest energy level possible. They're going to be as close to the nucleus as possible. So that goes with our principle about reading the periodic table like a book, left to right, top to bottom. You're going to start with 1s before you go to 2s. Okay? Hund's rule says that electrons will occupy each orbital with the same spin before occupying an orbital with the opposite spin. Okay, so you can look at it like this. When you're filling orbitals, let's say this is a 2p. Let's say the 2p represents a bus, and each orbital represents seats on the bus. Okay, if there are 3 open seats, the electrons are going to sit alone by themselves, just like you would, until they have to pair up. And so that's called the Hund's rule. They will sit by themselves, the electrons will stay by themselves in an orbital before they pair up. And the last rule is called the Pauli exclusion principle. And what that says is because that electrons have negative force and they repel each other, they will never travel in the same direction. They will always travel opposite. Okay, so you'll never have an orbital with 2 electrons with the same spin. You will never have that. They will always be opposite spin. Okay, so just to repeat, alpha would be the lowest energy possible, meaning when you read the periodic table, you start with 1s before you go to 2s. Okay, you go lowest, they fill the lowest energy level possible. Hund's rule says they'll occupy each orbital with the same spin before occupying an orbital with the opposite. Meaning, if it's like a school bus, each sublevel, they will fill each orbital with the same spin before pairing up. And then the last one says they have to have opposite spin. And you're going to represent that by an up arrow and a down arrow. So let's do some examples together, because I think that's the only way to really understand how to draw an orbital diagram. Okay, so you're going to draw an orbital diagram for a neutral atom of beryllium. Well, the first thing is you're still reading the periodic table like a book. So if you have your card stock with your 1s and your 2s and all that stuff and you still need it, you should be looking at that. Okay, so the first thing is to find beryllium. Okay, and beryllium happens to be in the 2s block. Okay, so you're going to start with 1s, that's at the beginning, and you know that each line represents an orbital, and s only has one orbital. Next, you're going to read across, and then you go down to the second row, and you are at 2s. Now, beryllium is in the 2s, so you're going to stop there. Then you're going to start to fill with electrons, and you know you need 4 of them, okay? So the first one is 1s, and there's only one seat on the 1s bus, so you have to fill it before moving on. Up arrow, down arrow. Now you need 2 more, so you're going to need to fill that as well. And that is an orbital diagram for beryllium. Okay, so let's move on and try a little bit of a harder one, carbon. Okay, Z equals 6. Carbon happens to be in the 2p group. Okay, that's where it ends up. So we're going to start by drawing our lines. We start at 1s, which has 1 orbital. Then we go to 2s, which has 1 orbital. And then we go to 2p, which has 3 orbitals. Remember, 2p has 3 orbitals, so we put 3 lines. Okay, then we have to fill them with our 6 electrons. So the 1s has only 1 seat on the bus, so we're going to pair it. The 2s has only 1 seat on the bus, we got to pair it, so that's 4. And now we need 2 more. So since 2p has 3 seats on the bus, they want to stay by themselves, so we're just going to put the 2 here. And now we've filled it with 2, 4, 6 arrows, which is signifying the 6 electrons. Let's do one more. Cobalt, Z equals 27. Okay, let's find out where cobalt is. And cobalt happens to end up in the 3D sublevel. So that's where we're going to stop. So we're going to draw our lines, 1s, 2s, 2p, 3s, 3p, okay, 4s, and 3d, which is going to have 5 orbitals. Okay, now I've drawn all my sublevels with my orbitals. Now it's time to fill them with electrons. I have 27 to fill. Okay, so I go up, down, no seats on the bus, so I have to keep filling. Okay, 2s is filled. Now 2p, I'm going to stay by myself until I come back and fill it. Notice how I fill it. I filled all up and then down, down, down. Okay, 3s, only 1 seat on the bus, it's got to get filled. 3p, up, 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 down, down, down. Okay, and I keep doing that until I get to 3D because I know that's where I'm going to stop. 4s, fill. Okay, let's count how many where we are. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I need 7 more. Okay, now watch how I fill the 3D. 1, 2, 3, 4, 5. Now I have to pair 6, 7. So this is an orbital diagram for cobalt, which is Z equals 27. Okay? So this is what's called an orbital diagram. And remember, you can also write what's called an electron configuration for it. It's just a different way of writing it. If I was writing the electron configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d, 2, 4, 5, 6, 3d7. And that's the electron configuration. I can also do the noble gas configuration for cobalt, and I would use the noble gas above it, which would be argon, and then it would be 4s2, 3d7. and that would be the noble gas configuration. Okay, and that's the end of this video. I hope you enjoyed it. Thank you.